Hi guys, can I get a shout out?
Hello.
Hi.
Hi.
Thanks guys. What do I want to do? Trying to figure out if I look crazier up close or far out. Or does it matter? Kevin was asking if we're going to have in-person classes in fall semester. And yeah, Armand says, yeah. I don't know. I'm just kind of like, it's been the 2020, I guess, taught me that you can't bet on the future too much. So I'm not sure.
Professor.
Yeah.
Have you posted Tuesday's lecture yet on Blackboard?
Tuesday's lecture on Blackboard. I thought I did.
I only saw up to last Thursday's.
Let me check. Just as I can't figure out what's going on in the future, I can no longer remember what's going on in the past. So I'm kind of in a, what happens when you get old? Let me see if I, just give me 1 second, guys. I'm plugging in, getting into Blackboard. Sorry guys, I actually have to play the YouTube. What was last Tuesday? It was, yeah, you're right. I don't think I have it on yet. Sorry guys, I'll put it up right away. I thought I had it on there. I'll put it up right after class. Yeah, last one I see is from February 4th, which I guess is last Thursday. So sorry about that. I'll put it up right after this class.
Okay, thank you.
Sure. Let's see what I have. Okay, any other questions, guys? No? Okay, then let's get started. So again, remember that there is a quiz 1 is on Tuesday. during the normal class. It might be 20 minutes, it might be 25 minutes, I don't know, something like that. It's not going to be very long, sort of the same length as the previous one. So let me just give a review of where we are. By the way, I know some of you guys, probably maybe most of you guys are confused about the concept of holes and maybe even mobile carriers in a semiconductor. I put a link for a YouTube video. At least the gentleman who's giving the lecture, it made sense to me, and it was pretty clear speaking, etc. I didn't see anything that, like many other lectures, that blew my mind, that like was going to clarify it perfectly. So hopefully you guys will will settle in at some point. Okay, so let's do the quick review here, which ends up usually not being too quick, but anyway. So where we're at, so the important point that we're interested in is we got to something called a p-n junction. Well, I don't know why I'm putting the slash. Usually you don't see a slash. It's just p-n junction. Okay, and you create that by taking some piece of silicon and adding donor type atoms to the n side and adding acceptor type atoms to the p side. So you create a p-n junction. And so I'm going to talk about just the important characteristics that I think you guys should just sort of keep in your head. So one is that because we had drift and diffusion currents, etc. So because of electrons moving from here, going to here, and holes going from here to here, the reason why they do that is because there's a lot of holes here, because it's a lot of, there's a lot of these acceptors create holes. So there's a lot of holes here. They want to go to where there are very few holes. The donors give off an extra electron. So those electrons go here. Once those electrons go here and the holes go here, you end up with the base atoms. So those, phosphorus atoms that gave up the electron end up being these positively charged non-mobile ions close to this junction. And say the boron atoms that gave off their holes or accepted an electron, say, basically end up being negatively charged ions on the p side. And what that does is it creates these stationary charges, create an electric field that goes from the positive side to the negative sides. Anytime you have a positive charge somewhere and a negative charge somewhere else, you'll get an electric field that goes from the positive charge to the negative charge. Okay, so that's an electric field that gets created. And whenever you have an electric field, you can basically also look at that. If you look at the electric field over a certain distance, you can see a potential energy difference. And so we call that voltage, from a circuit standpoint. So if you look at, definition of voltage is you integrate the electric field over whatever distance is. So if this was, whatever we call this minus x, we call this plus x, you integrate it from minus x to plus x, say, and you end up with a volt, and because there's a negative sign, you end up with a voltage here and here. Okay, and basically what this voltage is doing, because this electric field is pointed in this direction, it's actually fighting against more electrons going from the n side to the p side, and it's fighting against more holes going from the p side to the n side. So in a sort of equilibrium situation, the electric field and the voltage are exactly enough to stop any current from flowing from one side to another. So you get this thing, so without any external voltages or anything applied, just this thing sitting by itself, you end up with this voltage. And they call this the built-in potential or built-in voltage. So built-in potential. In semiconductors, they also call it potential barrier because it's stopping the flow of carriers from one side to the other. Okay, so here are the important things to remember about this. Okay, so this voltage, there's an equation for this voltage. It's KT over Q, natural log of NA times ND over NI squared. Okay, so now you have to kind of, there's a few things to remember about this equation. So this defines this built-in potential. Okay, one is this guy is equal to 25 millivolts approximately at room temperature. Okay, although these are all physical constants. K is the Boltzmann constant, T is the temperature, Q is the charge of an electron, physical constants. But, and because of that, you know, at a single temperature, which is, you know, 300 degrees Kelvin, room temperature, it ends up being around 25 millivolts. Okay, so as a circuit designer, that's what it is. You know, you have to live with whatever temperature your circuit's operating at. So you don't have any control over that. And then you end up with Na and Nd. And remember, these are the doping concentrations that we use to dope the N and P side. So these are doping concentrations of acceptors and donors. So these are doping concentrations. And N sub I is the density of mobile charges in silicon. And again, if we're at room temperature, this is 1.08 times 10 to the 10th electrons per centimeter cubed. Okay, so what does this practically mean when, you know, you're in the lab or you're designing with this PN junction? Well, like essentially, one is you don't have control over any of this stuff, really. Basically, some semiconductor engineer doped the PN to N junction before they sold you this device or whatever. So this is set by the factory. This is, you know, function of this being a silicon, mostly a silicon device. And the temperature is whatever temperature you're at. You don't really have that much control over it. So basically, all in all means you end up with this potential energy. And it's different for, like, if you go buy different diodes, they'll have different potential, built-in potential values, depending on essentially doping, depending on the doping concentrations. So here are some things to remember, key things to remember about V0. V0 things to remember. Okay, so one is that it's, you know, depending on the device you buy, the device you get. So somebody, let's call it the factory. Factory set NA and ND, and you don't have any control over it. So you don't control these. So what that means is, say in a problem for this class, we give you, like, if there's a question about, you know, calculating this built-in potential, you'll get ND and NA. Somebody's going to give it to you. I'll give it to you. Okay. Second thing is that this V0 is very temperature dependent. Okay, so just because, you know, so you're always very careful when you're designing a circuit. Whenever I talk, I try to always define, you know, what temperature is this at? Could be a room temperature. It could be, depends on, if you're building a product, what happens is, depending on that particular marketplace, they tell you, hey, I want this to work over these kind of temperatures. For example, if you're designing, maybe a consumer product, they might tell you, hey, from minus 20 C to 85 degrees C, this thing has to work. If you're designing something for military applications, there's a wider temperature range. Okay, the reason they tell you that is because this potential and this potential, along with some other things, change over temperature. So they're very temperature dependent. What makes it very temperature dependent? Well, look at there's two main things that are temperature dependent here. One of them is just temperature, just T. Okay, so straight up, it's linearly dependent on temperature. And then this Ni, if you remember the equation from Ni from a couple of classes ago, it was very, very, very dependent on temperature and, exponential ways, et cetera. It's getting a natural log put on it now, but it's still Ni squared of an exponential-ish thing. It gets a natural log, but still, very temperature dependent. So anyway, be very careful that it's defined at a particular temperature. Okay, 3, because of the natural log, because of this natural log function, there's it's hard to make this too high. There's like kind of a set range. There's a common range. Okay, and that's like maybe between 600 millivolts and say 900 millivolts. It's not going to vary much more than that at room temperature. So you're not going to see a silicon diode with a 2-volt potential barrier, or a 200 millivolt potential barrier. This is kind of the range, and again, it's going to depend on really the factory, what they did, and kind of what temperature. Okay. Okay, so those are the things to remember about this built-in potential. Okay. Second thing is that was all without any external voltage applied to this device. So we're in a circuit design class, and what we do is we build these things and apply voltages across them, put currents in them, etc. So that's kind of our next step, is what happens if you apply a voltage across this thing. Well, so this thing, remember I was telling you guys when we first started the class that, like, let's say if we just think about a resistor, right? A resistor with a voltage across it. Okay, and this is some resistance. If you plot the voltage versus, so I put this voltage here, current here. The resistor is a linear device. Okay, so if I increase the voltage, I get more current. If I decrease the voltage, I get less current, and it's all defined no matter where I am, at a very positive voltage, very negative voltage, no matter where I am, everything runs with this V is equal to IR equation, with this being 1 over R is the slope of this. It's a linear device, okay? But this PN junction isn't like that. Is not. So PN junction is not a linear device, which actually is kind of makes it interesting. And neither are transistors, neither are sort of any other devices we talk about here, because they depend very strongly on how you apply the voltage. Whether you do a positive or negative, they act very differently. So let's say you took your PN junction Okay. And so, I'm trying to draw it in the same way. So there is a built-in potential here. Okay. So you can do two things. One of them is you can put, let's say I had a battery and I was applying an external voltage here. So the external, and there's already a built-in potential here. So notice that if I put my battery like this, with the positive side hooked up to the N, and the negative side hooked up to the P, it's hooked up in the same direction as the built-in potential. Means that it's increasing so it's helping the built-in potential, let's say. It's enhancing this barrier. It's increasing this barrier, meaning that it's like it's not going to encourage current flow. Okay, so this is called reverse bias when I hook it up like this. Bias. Okay, so this, let's say it increases the barrier to current flow. Okay, so now let's say I take the same dude and P, and it has this built-in potential, and let's say I reverse the direction of this voltage. Okay, this is an external voltage. So, and then I start applying that. Notice now this external voltage is working against the potential barrier. Okay, and so as I increase this, it's reducing this barrier. So it's reducing this barrier to electrons and holes flowing. So it means that as I increase this voltage, when it's hooked up this way, I start getting current flow because the barrier is getting reduced. Okay, and this is called forward bias when it's connected like this. Okay, forward bias is when you apply an external voltage that's you put your positives, put more voltage on the P than you do on the N side. Okay, that's called forward bias. You get a lot of current when you do that through this device. And then reverse bias is when you put the N side more positive than the P and you get almost no current flowing in that case. So it's almost like an open circuit in that case. Okay. So that's what I want to say. And so again, this like current flow when you're in this forward bias is very, very fast. This external barrier. So let me see. Well, let me keep going here. Okay, any questions? I think that's sort of summarizing all the stuff that's very important.
Professor?
Yeah.
Oh, go ahead, Nelson.
No, you. Oh, you sure? You okay?
Yeah.
No, it's just a quick question. So you said that if you, I think for the forward bias, right? You said that it's like an open circuit. So then, if it's like an open circuit, then wait, where's the open circuit coming from? You mean the wires themselves, or? Like,
Yeah. So actually, the reverse bias is the open circuit.
oh, the reverse bias open circuit. Okay.
Reverse
Yeah.
bias.
So does that if it's gonna be open circuit, then does that mean it's like not like how to say it? Doesn't that mean like is there a point in having this voltage then, or?
Yeah, you'll see. You'll see. So what happens is, let's see, how can I? It's like sort of bear with me, and you'll see what. So for right now, we're sort of defining this element, the circuit element, the PN junction. And in chapter 3, we're actually going to start designing circuits with it. So, and the circuit we're going to design with it is like a power supply for your laptop. And you'll see that basically having a circuit element like this which conducts in one direction and doesn't conduct in the other, actually allows you to go from an AC supply like you get from the wall. The wall supply is jumping around between, I don't know, plus minus 140 volts, right? It's 110 volt RMS, but it's plus and minus, plus and minus. If you hook that up to your laptop is gonna blow up. So somehow you got to change that from that plus minus value to say a plus 12 volt. Yeah, exactly, a rectifier. David put his finger on it. So if you want to get it to a DC voltage, positive DC voltage, and it's this circuit, basically what it does is it cuts off the negative voltages and only allows in positive voltages. And it's kind of the first step in creating that DC voltage. So that's one of the many uses for a circuit that is an open circuit under one voltage polarity across it, and it's a short circuit across another voltage polarity. Does that make sense?
I guess so, yeah.
So let me draw it for you. So let's say you had this. This is the. Whoops. So this is something that's coming out of your wall. Okay. So this is time. This thing is 110 volt. Root mean squared, which means, I don't know, the peak is like something like 140 volts. And this dip is minus 140 volts. Okay, if you put an oscilloscope on your wall plug right now, it's kind of what you see. And you'd see this cycle is, I don't know, it's like, oh, sorry, this is like 16 milliseconds. No, is it 16 milliseconds? No, it would be 8 milliseconds roughly. Okay, are you with me so far?
Yeah.
Okay, that's just what's coming out of your wall. So what your PC wants to see, I don't know how to draw a PC. I don't know, is something like this. Time. It wants to see something like this. It doesn't want to see these ups and downs, ups and downs. It doesn't work with that. It wants to see that. So somehow you got to build a circuit. And in fact, that brick that you get with your laptop, you plug into the wall, it's doing this. It's taking this voltage and turning it into a DC voltage. Okay. Now this voltage, are you guys familiar with AC versus DC and all that stuff? Just AC is just something that it's, alternating current. It changes with time, and DC is something that doesn't change with time. Are anybody confused about that? Everybody's good with that? Okay, so something like this that is positive. This is positive, the same amount of time that it's negative. Okay, so it's negative for exactly the same amount of time as positive. And so if I look at the DC voltage content of something like this, I get this has 0 DC voltage content. So as it is, I can never take as it is. I can do anything I want with this. I won't be able to get this. I need some DC voltage content here. This has no DC voltage content. So what do? Well, okay, if you use a diode, you can set up a diode that it is reverse bias here, means it doesn't conduct there, and it's forward bias here. So if you put this across a rectifier, which is a diode that does that, what you'll see is this. It'll let the positive go, then it won't let any of this go, and then looks like this. So 140 volts. So I just cut off everything below 0. Now this has a DC component because it has a certain positive voltage component, but doesn't have any negative voltage component. So if I integrate this over a cycle, it'll have a DC component. So if I put a capacitor, anyway, you guys will see the details, and we'll get into the circuit in some detail. in chapter 3, so starting next week. If I can, this is a starting point for me to be able to get to create this DC voltage from the wall. So, and that's what that, so we'll see how that brick that you use to charge up your PCs, et cetera, gets made. And if you did not have a PN junction, you just couldn't have that function. Okay. So bear with me about the uses of this device and all that stuff. But so right now we're just sort of building up with what this device is and what it looks like. But you'll hopefully start seeing some of the stuff you can do with it. Any other question?
Yeah, Professor, I got a question.
Yeah.
So these PN junctions, they're diodes. Can we view these as, do they have a equivalent resistance or impedances? Because in reverse bias, it doesn't allow any current flow. So is that like infinite impedance?
Yes, 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 exactly. So I'll if you bear with me, Melvin, in like 4 slides, we'll get to the different sort of ways of looking at impedance, et cetera. So hold that thought, because that's where we're going.
All right, thanks.
Okay, so we had this forward bias and reverse bias. Okay, again, this is going to be very, very useful as a device, and it's also a building block for transistors, which are even more useful, but anyway, we'll get to those. Okay, so so Melvin got us down this path of this, and we might have mentioned this earlier, is that so this PN junction, I'm going to just flip the P in the end just because it's PN junction. Okay, so this thing is a PN junction. So who calls this PN junction? Semiconductor designers call this PN junction, mostly. This exact device, the same thing, PN junction, is called, circuit designers call this a diode. Okay, and they draw it, this is the schematic symbol for a diode. This is what a resistor looks like. This is what a diode looks like. And this is the N side, and this is the P side. Okay, and so, don't ask me why, PN junction diode. And then here we had the built-in potential. Called, V0. And in diode, we call it V sub D, on. Okay, so same thing. PN junction is the same thing as a diode. Built-in potential is the same as the VD on, as you'll see. Okay, so now let's say now we're getting along the path of, okay, what do we do with this stuff? What does it look like as a circuit? Let's say start looking at it as a circuit function. So let's say I have a voltage source. I hook up my diode like so. So we have our VD here. Call this I sub D is the current going into the diode and coming out of the voltage source. And this is, let's call this Vx, I guess. Okay, which is going to be the same. Vx is going to be the same as VD, right? If you do a KVL here, VD minus VD, Vx minus VD is equal to 0, so Vx is equal to VD, right? You can visually see that with its fraction. Okay, so what does this look like? If I plot this thing, okay. So let's say, let me do this because it's a little, I feel like it's not giving me enough space. Okay, so let's say I V sub X is a very, very negative voltage. Okay, so I have a very negative voltage here compared to this voltage. Okay, so this, if I have a very negative voltage here compared to this, it puts the diode in reverse bias. It's adding to the built-in potential. So if I'm out here, this guy is essentially off. As I can change this voltage all I want. It's not going to do anything. It's just going to be, there's a little bit of leakage current. Okay, this is called I sub S. And, you know, this is where Melvin was going. This I sub S, this leakage current, is something like 10 to the minus 10, depend on the diode, to 10 to the minus 17 amps. So like a very, I mean, you never get zero current, no matter how open you think a circuit is. There's always some like something, some leakage, something happening. This is very, very little current flows, okay, through this diode. And as I keep, let me just draw this in red so you can see it. So this is very, very small. And it's a negative value. So it's minus I sub S here. So put the minus here. Okay, it's below the zero of the current. Okay, so now as I keep increasing the current right at zero voltage, I get just zero current, exactly zero current. Okay, and as the voltage keeps increasing, I start getting this diode into forward bias, because what happens is now, as this voltage starts getting positive, I'm putting more positive voltage here than I do here, more positive voltage on the P side than the N side. I am reducing the potential barrier, and so I'm starting to get current flow. And in fact, like I said, the current flow is very, very fast. In fact, it's kind of exponentially dependent on the diode voltage. Okay, so and we'll see how. So this is, let's just say, proportional to. I'll fill that out in a second. So this I sub D in this area is like very, very rapid increase in current, very, very rapid. Okay, so what does this equation look like now? Okay, so now this is the part, like if you're just being as, you know, if you got your circuit designer hat on, this is the only thing you'll kind of like tend to remember, is this curve that describes this diode voltage versus current relationship. Okay, so remember a resistor, it had the current voltage relationship was just V is equal to IR. Okay, or I is equal to V over R. Here, if I draw this, write this equation, I end up with a more complicated equation. It ends up being I sub S, okay, same as this guy, exponential of V D over VT. Oops, I always put the parentheses in the wrong place. Okay, sorry guys, let me write this up here. So it's parentheses exponential of VD over VT minus 1. Okay, so this equation describes this device. So it's the equivalent of this for a resistor, it's this for a diode. Okay, so this is the voltage across the diode. So what are these other components? Okay, we got VT and we got I sub S. Okay, so those are two parameters that we need to define. And then we got this exponential characteristics. Okay, so VT, again, remember the circuit designers and semiconductor designers have slightly different lingo. VT is our KT over Q. That's just a definition of VT. and this is approximately 25 millivolts at room temperature. Okay, so Boltzmann constant times temperature over Q. So it's a, you can think of this as a constant that's temperature dependent, V sub T. Okay. I sub S, we defined for a junction as, you know, previous lectures as, you know, we had a complicated equation for it, AQ NI squared D sub N over NA over Ln plus dP over ND LP. Okay. So when you're a circuit designer, as far as you're concerned, this is also a constant. So let's say you buy a diode or something like that. The data sheet, the spec sheet will tell you what this I sub S is. Why? Because, okay, this is the cross-sectional area of the diode. Okay, so this is a diode area. So, you know, somebody back in the factory put this diode together, so they made the area. Okay, Q is the charge of an electron. God, I'm really writing small here, hopefully it is. Okay, so physical constant. Ni is this density of free carriers in silicon. Again, remember it was 1.08 times 10 to the 10th per centimeter cubed, again at room temperature. So again, a constant. And then the rest of this stuff, D sub N, D sub P, and DLN, and DLP, these are all stuff that the factory made. You know, they doped this diode, the N and the P side, a certain way. So most of the time, you just look at this as a constant value. So, and you know, it's a very, very small number. So again, I wrote it here. Most of the time, this I sub S might be, you know, might be range from when it's very high, 10 to the minus 10 amps, and when it's very low, might be 10 to the minus 17 amps. So a very small number. Okay. So this is the sort of the God equation to remember. Yeah.
Just double checking, the -1 isn't part of the exponent, is it?
It's not. Yeah, sorry. I'm trying to figure out how to best make it clear. I don't know, like that. It's not part of the exponent. So if you look at it's a very good question, though, because it's easy to get confused. So if you look at this equation, notice what happens when V sub D is very negative. Let's say it's minus 100 or something, I don't know. So this ends up being the exponential of a very negative voltage. So the exponential to a very negative voltage ends up being 0. So this whole expression ends up just being 0 minus 1 or minus 1. Okay, so out here, this is just part of the equation is just minus 1. And you get minus 1 times I sub S, and you end up with minus I sub S here. Okay, when V sub D is 0 here, okay, V sub D is 0, exponential of 0 is 1. So you get 1 minus 1 is equal to 0 here. So you get 0 times I sub S, you get exactly 0 current. Okay, and as V sub D gets positive larger and larger, what happens is this ends up being an exponential of a positive voltage. And so remember, V sub T isn't very much. It's only 25 millivolts. Okay, so let's say if this V sub D is 250 millivolts, this is like exponential to the 10th, which is a gigantic number. Okay, so very quickly, this ends up being much, much higher than minus 1. Okay, so here, out here, you can call this positive side, and we always do. So this ends up being when you're in forward bias, I sub d is approximately, you can think of it as being I sub s exponential of vd, vd, yeah, vd over vt. Because the -1 just is just so small compared to what this exponential value ends up being, okay? So those are the two regions you sort of have, sorry, three regions. You've got three regions here, okay? You got this region of very sort of negative, anything below 0 volts, when V sub D is below 0 volts. This is all reverse bias, okay? And basically, the current is almost 0 here, okay? So I sub D is, you know, approximately 0. It's really minus I sub s, but it's pretty close to being 0. Okay. Then you got anything like out. So this is anything here, anything out here. So I don't know what that number is. Pick your pick, 100 millivolts, 50 millivolts, whatever. It's basically I sub D has this really exponential behavior. So it rises very, very rapidly. I don't know how to, I think you just have to plug in the numbers in Excel to see how gigantic this gets very quickly. If you have time, I'll go through a example, and you guys can see how the current just jumps. It's just really like a short circuit. Okay, looks like we just have a short, like a switch thrown. And in fact, this is sort of like one model of how to look at it. And in between here, sort of this is the range where, you know, below 25 millivolts, below 30, 40 millivolts, you pick it again. Depends on the application. You have to use sort of the full equation. But usually you're either using this equation or you're just calling this the current across the diode 0. Okay? Any other questions there? Or anybody else? Anybody good? Okay, so remember, this is the important stuff. This is very, very, very important. Okay, this equation is very, very important. And these facts are very important, that in reverse bias, when you got a negative voltage across the diode, the current 0. In positive bias, you got this sort of exponential behavior that's very, very rapid. Okay. Hey, as promised, so I'm gonna let's run an example here, okay? So this is also example 2.19 from the book. If you guys wanna look at it, maybe better explained there. So the question is, if I have a diode in forward bias, so if forward bias, okay, so basically if I have I sub D, remember in forward bias, I can use this approximation for the diode current. I can just get rid of the 1 in forward bias. So I can use I sub S, always should put in squiggly here, exponential of VD over V sub T. Okay. How much do I need to increase, V sub T to get 10 times I sub D? Okay, so I want to go, like, I want to increase, the question is, I want to increase the current across the diode by a factor of 10. How much do I need to vary the voltage across the diode? Okay, so this example is trying to show you how rapid an increase this is. Okay, so let's look at it. And this also shows you some of the, like, it's not very complex math, but it's some things you guys need to remember from the from your math classes, I guess. So, okay, so this is how you solve this problem. But the gist of it is you don't need a lot of voltage to get a lot of current. Okay, so let's say initially, let's call that VD1. That's our initial voltage that gives us the baseline current. Oh, let me tell you guys one more thing. Sorry. Did we define? I don't think I ever defined this thing here. V sub D. Ah, okay. Yep. So like I said, this before I say that, let me just say this. So this is like an important equation, right? It's for bias diode. So this gives you the current in terms of the voltage. Okay. Another thing that's really good to remember, because you don't want to keep, you need to keep going back and forth between, you know, current, voltage, voltage, and current. So the other thing to remember is just reorganizing this to look at V sub D as a function of I sub D. So I'm just moving stuff around here, okay? So it ends up being VT natural log of ID over I sub S. Okay, it's the same equation. Okay, but in this is when I have V sub D and I want to get I sub D, when I want to get the current and I have the voltage. This one is when I want to get the voltage across this device if I have the current. Okay, just you're gonna have to remember both, but you can drive one from the other, no problem. Okay, so now, having said that, so the initial voltage across the diode is VT natural log. So this is the first current, and we want to get 10 times that current, but initially we call it ID1 over I sub S. Okay, so then in the second case, VD2 is VT. So remember again, VT is around 25 millivolts at room temperature, but the exact value is KT over Q, which again are a bunch of physical constants. Okay, but you will not go far wrong if you just remember this. Okay, so this is a constant. I sub S is usually given to you. It's not necessary to solve this problem, but normally it'd be given to you. Okay, unless the problem is figuring out I sub S. Okay, so VT natural log of 10 times ID1 over I sub S. Because we're saying we want to figure out VD2 when the current's gone up by a factor of 10. It doesn't matter what it was to begin with. It matters that it's increased from the earliest value by 10 times. Okay. Okay, so this, we can put this, so the way natural log sorts out is this is equal to the natural log of ID1 over I sub S plus VT natural log of 10. Okay, straight up math. Okay, so now let's look at this. So we got these two terms. So this is the voltage that's required to increase the current by 10x. The first part is just our initial voltage, right? This is the same as this. So that's our initial voltage. Okay, plus, now let's look at this. This is 25 millivolts. This is natural log of 10, which is 2.3. Okay, when you multiply those two together, you end up with about 60 millivolts. Oh, sorry, multiply them together, yeah. Okay, so what does this tell us is that to increase the current across a diode by a factor of 10, you only need to increase the voltage across it by 60 millivolts, okay, which is a pretty small amount of voltage. Okay, so what this tells you as a circuit designer is this is an incredibly steep curve. Okay, just by increasing the voltage by a little bit, the current goes up by a lot, okay? And it's doesn't matter what your initial current was. It could be that you're going from 1 milliamp to 10 milliamps. So you add 60 millivolts from the voltage that you were having when it was 1 milliamp to get to 10 milliamps, or if you were going from 10 milliamps to 100 milliamps, you add another 60 millivolts on top of that, because it's sort of it's an exponential relationship. So you're adding incrementally very little voltage, and you're getting a huge amount of current increase. And you see that in the exponential curve here, right? So you're adding a little bit of voltage. Okay, if my voltage goes from here to here, my current increases a lot. My current increases a lot. Same increment is giving me huge increases in current. By the time I get here, God, I don't even know. Like every 60 millivolts step here gives me a 10x increase in current here. It's like very extreme. Okay, any questions about that? But incidentally, it's not as important as the other things to remember, but this business of if you want to increase current by a factor of 10, you add 60 millivolts across the diode. Yeah, it's kind of useful to remember it, but anyway, this is the constant value. Any questions about that? Again, it's to just demonstrate that this is a very steep curve of current versus voltage. Okay, so now let's, where are we? Oh, good. We're almost on schedule. All right, so here's another example. Okay, about what's not so nice about this diode equations. Okay, which leads us to the next thing I'm about to say. But okay, so let's say so far we just had, a diode and a voltage source. Okay. There's a current going through. Okay, great. So that's so far that's what we saw, right? So the simplest addition you could do to the circuit is just let's add a resistor. Like it's just like real circuits are a lot more complicated, but if I was just gonna do like the simplest thing I could do, right? But that I don't know what else to do that would be simpler. You add a resistor here. Okay, so you get the V sub D here. And now let's call this guy, I call it I sub X. Okay, so let's see, I wanted to find it. Okay, so now we assume room temperature. So let me give you a spoiler about this example. So this example is supposed to show you how complex having something like this makes circuit analysis. When you have these exponentials and when you had resistors, it was pretty simple equations, right? I is equal to V over R, whatever. When you have natural logs and exponentials, etc., it gets like the math gets crazy fast. Okay, and so this is supposed to show you why that is. And this is a build up to the next thing, which I'm about to say, is about how we can simplify these equations. Okay, like what assumptions we can make to simplify these equations. So that's a spoiler, but let's bear with me for a second. So assume we're in room temperature. So calculate I sub X for V sub X is equal to 3 volts. And the other assumption we can make is I sub S is 10 to the minus 16 amps. Okay, I'm gonna be cruel to you guys. Once you guys take a shot at trying to figure out this thing, so remember you want to calculate I sub x, and so is V sub x is 3 volts, and I want to know for that what value I have for I sub x. Once you guys give a shot at that, and then I'll ask one poor individual to help me try to solve it. Okay, guys, let's try to give it a shot. So I'm just gonna pick I think it was the last person who spoke. Darren?
Yeah.
Do you dare?
Yeah, I'm here.
Nice. Let's do this. So how far did you get?
Not very far. I know that we can use the KVL.
Okay, good. Good stuff.
Vx equals Ix times Rx.
Mm-hmm.
VT ln VD over VT.
Sorry, can you say that? Plus?
Plus VT ln of VD over VT.
Now we got to be careful here. It's actually look at this guy.
Yeah, it should be what is that? Ix over Is.
Exactly. Good one. Ix over I sub s. Okay, right? Dead bang on. So where do we go from here? So this guy's 3 volts. Oh, and then sorry, Rx is 1 kilo.
And then we can do use the natural log rules and do VT ln of Ix minus VT ln of Is.
So you're gonna do VT ln of Ix minus VT ln of Is. Like that?
Yeah. And then that's as far as I got.
Yeah.
I'm a little confused here on VT. Is VT the voltage drop on the transistor?
No, we don't have a transistor here. Remember?
Diode, my bad.
Yeah, VT is a temperature dependent constant, KT over Q, or about 25 millivolts at room temperature.
Okay.
V sub T, you can just think of it as a constant for most of what we do For most of what we do in the class, it's a constant. Just beware that in the real world, it's temperature dependent.
Okay. Yeah, got it.
Okay. So guys, this is like the what do you call it? This was a leading question because there's a reason why an intelligent man like Darren, an intelligent Cal Poly student, electrical engineering student, can't get much further with this, is because there's no closed solution for it. You could just stare at this all day long and you're not going to find a closed solution for it. Okay, so the way to solve this thing ends up being you take a guess for V sub D. This is just this hokey, this is it. You take a guess for V sub D, you plug it in to this equation. Okay, you get a value for I sub X. You then plug that back in, get another guess, get another guess, get another guess, and hopefully things are converged. So let's look at how that's done. Okay, and there's some problems hopefully in the homework that shows you how that's done. So I'm gonna deviate from here slightly. So I'm gonna start from back from here. So Vx is I sub x r sub x plus Vt natural log of I sub x over I sub s. Okay, or you just call this V sub d. Okay, so the one thing that comes to our rescue, okay, now remember V sub d is the built-in potential. Which is the same as V sub 0. And if you guys remember, V sub 0 is, well, maybe you don't remember, is sort of V sub t. Again, this is like KT over Q. KT over Q. Natural log of this fruit salad, ND over NI squared. Okay? And if you guys remember, what I said was because of this natural log function, this whole thing, and this is 25 millivolts, you can, for the sake of this, for the room temperature, because of this natural log, no matter, you can, natural log function looks like something like this. It goes like that. So it like sort of peaks if I have X and then natural log of X. So no matter how hard I try, no matter how hard the guys in the factory try, you can't get any old number for here. So this, this is limited to, I don't know, like 600 millivolts to 900 millivolts. Okay, like you're not going to see again a silicon diode with even a V sub D of like, I don't know, 1 volt. Okay, remember if you get so the V sub, look at what happens here is, see, when you put a positive, let me take it one step back. You put a positive voltage here, right? Put a positive voltage here. There's some voltage drop here depending on what I sub X is. So it means that you'll get some positive voltage on the P side of this diode compared to the negative side, okay? Which means that it's in forward bias. Everybody with me? Forward bias, okay? Which means that we're sitting here somewhere, okay, out here. And here, you cannot get a significant change. You can basically, this current can be very high, very low. This V sub D is not going to change very much. Okay, it's just not going to change very much. As soon as that diode is on, it's like V sub D is almost a constant. Okay, this is like, this drawing doesn't do justice to how fast this curve is rising. Okay, so it's almost like this thing just stays on this value. So what I can do then is I can take a guess as to what V sub D is. So, and in this class, a good guess is, for most problems, a good guess is, 750 millivolts or 800 millivolts as a starting point. okay? And then I basically plug that into this equation. This is 3 volts. So I sub x is 3 volts minus, let's say I guessed 800, let's say I guessed 750 millivolts, because that's what I guessed in my notes, over R sub x, okay? I get some value. I get an I sub x of 2.25 milliamps. And okay, so I get that, but what does that mean? It's just, oops, this just was based on a guess. So now what I got to do is plug this back into the equation. So now I'm like doing this sort of recursive thing over and over again. You'll get used to doing this in this homework and the next homework. I guess I'm going to plug I sub x back in to the equation for V sub d. Okay, so V sub d is Vt natural log of Ix over I sub s. So is equal to 25 millivolts natural log of 2.25 milliamps over, they gave me I sub s, 1 times 10 to the minus 16 amps, and this V sub d ends up being 799 millivolts. So it's like, uh-oh, okay, this is not the same as my initial assumption. Okay, so that didn't quite work out. So let's plug this V sub d, maybe that's the right number. Okay, we plug that V sub t back into our equation for I sub x. So I sub x is 3 volts minus V sub d over R sub x. So now we do 3 volts minus 799 millivolts over 1 k ohm, and we get 2.201 milliamps. Okay, so it's not moving. So it's getting, so it looks like, you know, the V sub d of 750, our initial guess gave us an I sub x is 2.25 milliamps. This second one is giving us 2.201 milliamp. Okay, so again, we plug that back in. So this is iteration 1. This is iteration number 2. Okay, so V sub d is V sub t natural log of 2.201 over 1 times 10 to the minus 16 amps, and that is equal to 0.768 volts for V sub t. Okay, which is kind of getting closer to our original value. So if I look at, like, if I draw this as like iteration 1, iteration 2, iteration 3, so I can keep going like this until, like, you know, stuff converges hopefully to the actual V sub d. Okay, so you keep doing these iterations. There's no closed form solution for solving this. Okay, so I keep doing these iterations till I converge to some V sub d. So like between iteration 5 and iteration 6, V sub d between those two iterations only changes by like a couple of millivolts, say. Then I say, okay, I'm done. This is like, it's an iterative solution to this problem. And the reason why it's sort of, I wouldn't sort of practical, is because V sub d values, they, you know, it's a limited range. We know, you know, it's not going to be 2 volts for our initial guess. We know our initial guess isn't going to be 100 millivolts. We know if we make an initial guess between 700 and 800 millivolts, that's like a good number for a typical diode. Okay, that's why you kind of get away with this iterative procedure. Okay, so you'll get some level of practice with this from the homeworks. Okay, so this example is trying to teach you 2 things. Okay, one is that this iterative method. So if you're using this, you're using this type of equation, you can use the iterative method to get to a solution. Sometimes you just have to do that, okay? And we'll look at examples where you have to do it. But it also is supposed to show you what a pain in the butt having this equation is. Like like I started this example by emphasizing what a simple circuit this is. I just added a resistor to a diode and it turned into a mess, right, with natural log. Imagine if I had another 3 diodes here, some resistors, some capacitors. Like it's like just a simple circuit would end up being a mathematical nightmare to solve. Okay, so those are the 2 things it shows you. Okay, so electrical engineers being the practical people, like, hey man, we got to get our design done. We're not like physicists. We got to get this stuff done, get paid, go home, you know, the customers got a deadline, etc. So what do? Okay, to solve that second problem is they came up with a really simplifying assumption. And this is going to confuse you guys, but I'll keep going over this over and over again, okay? So the real current equation, I'm just going to rewrite it, is I sub s exponential of Vd over Vt minus 1. Okay, this gives us this curve. This is minus I sub s. This is Vd I sub d. Okay. So cool. This is like a good equation, accurate, but it's kind of a pain to use in most circuits. So what your forefathers did, electrical engineers, they figured out that for most cases, you can do a really cheesy assumption here, which works really well. Okay, and this is the assumption. This is a simplifying model. It's called the constant voltage model. Okay, so this is just a simplification of this whole thing. Okay, it's not in opposition to, it's just a simplification, so it makes circuit analysis easy for the most cases. Is to approximate this exponential, so draw the exponential curve like this. So this is a complicated equation. So what they did, our forefathers, they said, okay, I'm just gonna say instead of that, this is how it works. Okay, so here, I'm not gonna have, this is, says minus I sub, here I'm gonna say 0. Okay, here it says, you know, exponential whatever, I'm just gonna call this resistance equal to 0. So this is, remember, this is a straight up line. So resistance is 0, resistance here is infinite. And this all happens at like 1 voltage. It's not like it's something that moves fast, it just happens dead bang on. So what does it look like? So it looks like our diode, okay? Then V sub D is less than VD on. So when I'm out here, this diode looks like a open circuit. Okay. So it's maybe somewhat going back to Nelson's question. So here, it just looks like an open circuit. Again, this is simplifying assumption. No minus I sub x, no nothing. It's just an open circuit, no current, nothing. And as soon as I get to VD is larger than VD on, larger or equal to here. Okay, so anywhere here. Doesn't matter how, I can be as high up as I want here, the current's gonna stay the same. So it's gonna, the diode is gonna look like a short circuit. No exponential, no nothing, just a short circuit with 0 resistance. Okay. And it's gonna all happen on exactly on VD, this voltage VD on. Okay, A voltage, which is at 750 millivolts or whatever it is, okay? So this is again, I'm emphasizing this. This is exactly the same device as this, okay? It's just that a lot of times, you can make a very simplifying assumption to figure out what your circuit's doing. And we'll be doing a lot of that in chapter 3, the next chapter, okay? So guys, I'm gonna stop here. Any questions?
Professor, I had a quick question. Can you go back to question 2.19?
Where was it?
Yeah. You just passed.
Yeah.
Yeah, right here.
Mm.
So do you see VD2?
Yeah.
So the step after, I kind of like got distracted. I don't know what happened.
From here to here?
Yeah.
Yeah, it's just that if you have a natural log of say x times y, you can rewrite that as natural log of x plus natural log of y. So that's all that happened in that step. So I had
Okay.
natural log of.
Yeah, that's what kind of I missed when I was distracted. Thank you.
Sure. And then if you have natural log of x over y, it's natural log of x minus natural log of y. So there's not a huge amount of math in this class, but like this stuff, you just have to kind of like remember a little bit. It helps. Any other questions, guys? Okay, if not, remember I recommended highly for you guys to do the homework, although it's not guaranteed that all the questions from quiz 1 are going to come from homework 1, but it's going to be enormously helpful if you guys do homework 1. It's my recommendation for you guys. And then also remember that office hours is tomorrow between, I forget. We'll both have to look it up on Blackboard if you guys got some questions. All right, guys, good luck. And I'll see you on Tuesday. Take care.
Thank you.
Thank you, Professor.
Thank you,
Thank you.
Professor.
Thank you, Professor.
Thanks.